didn't fill it out yet. So before I start the lecture, I just want to clarify something with the class and emphasize something. So when we have like our homework assignments and quizzes due at a certain time, they are due at that certain time, right? And usually I post the homeworks on weekends. I try to do it like Friday night, but sometimes it would be like, Saturday or Sunday. But regardless, you will be having that like Sunday at some point for sure. And also you have like, Monday, Tuesday, Wednesday, 3 days to work on them. And they are just like from the lectures, they're like, straightforward, and you're welcome to use all the materials that you have. But you should learn them afterwards, because in the exam you don't have any of your course materials. And also quizzes, usually, after we're progressing with the lectures, previously I had them scheduled like, after every 2 chapters, but as you can see, we're not, progressing as much as I wanted with the course, but we still stick to the schedule on the course syllabus. And you have those dates there, they won't change for like homework assignments, quizzes, and exams. And also, I gave you a homework assignment asking when are homework assignments due, right? That they are typically due on Wednesdays most of the time, unless we are on spring break and then Wednesday is off, right? And also for quizzes, they usually do on Fridays, and you have all the dates there. So last semester, because I joined University of Idaho in the middle of the semester, I was really lenient in my Chem 101 class, and I think now there might be some misperception that if you miss a homework, that's fine, we're gonna work on it at the end of the semester or something. But this is not the case from now on this semester, because I have everything predetermined. I'm just like lecturing myself throughout the semester. I know what I tell you and what I ask you. So all that things being said, I had students, in both my classes, that they emailed me that we forgot about the quiz. Can we have like a makeup quiz? And I'm like, I didn't know how to answer that, because if I do that for some students, it's unfair towards other students, right? There are like some of you that you took the quiz, you weren't prepared, but you took it anyway, and maybe you didn't have the score that you wanted. So if one student emails me and they ask for another version of the quiz, it's unfair towards the other students. And if I provide opportunity for all students to take the quiz again, I can never progress with the course, because I just should do makeup homeworks, makeup quizzes, grade those, and we're not progressing with the course, right? So now what I'm going to do for the previous homework assignments and quiz 1, just this one time, I'm going to have like a makeup session this Friday, 4 p.m. And I probably better to write this. Like Friday, 4 p.m. And I think I talked with Deb to have like the room rent through 111, because it's a big room, but I should check on that. So stay tuned. Next session, I'll tell you if that's a room or not. For anyone who didn't have a good grade on their homeworks 1 to 3 and also quiz 1. Again, I'm doing that because I should be fair towards all students. So if someone just like didn't do the quiz, right, and then they reach out to me and I give them another chance, I should give all of you a chance to be fair towards all of you. But this is just like one time, so it would be like makeups for these. So it won't be the same questions, it would be makeup. And you cannot use any of the course materials, because they're already passed due, and for your exam you should know all the materials, so it would be like closed book. But this is like the only time that I'm making this exception, because as I said, some students were confused about like my teaching style, or like, I don't know. And I want all of you to succeed, but again, if I just like have like makeup homeworks, makeup quizzes, I cannot progress with the course, okay? Any questions about that? Yes.
Are you taking the highest score or the one from the makeup?
I compare the grades and consider the highest one.
Okay.
But as I said, this is like an exception this time, because when the students reach out to me that, and then they have like, some students have valid reasons too. But, after the quiz is not the time to communicate that with me. I have students that had like medical reasons and they missed like several lectures and they emailed me before the quiz is due, can I have extension? And I don't expect you guys, if you're ill in your bed, you cannot work, to do CHEM275 quiz. I don't expect that. But you should communicate that with me in advance and I work with you, okay? But literally when like, there's 1 hour left to the quiz and then you tell me I was in hospital today, I'm like, you could have worked through it beforehand, So again, if you cannot meet the deadlines, you should communicate that with me in advance, like absences that you do, right? I will miss a class because I have a family emergency. Okay? Are we clear on the homework and quizzes? So from now on, if someone like on Saturday emails me that, I saw your email late, and this is another thing, you might have noticed that, just like 4 hours before the deadline, I look through Canvas, I see who missed the assignment, and I emailed them individually because I don't want all the students receive like multiple announcements. And last semester, students were getting like 2-3 announcements per day sometimes. And that was one of the things that the students mentioned in course evaluations, that they don't like to have like so many announcements. So now I'm trying to have minimal number of announcements. So I reach out to them, just remind them you have 4 hours to do the homework or the quiz. And then if you reach out to me the morning after that, I saw your email late, it wasn't my responsibility to send you the email in first place. Does that make sense what I'm saying? Okay, so hopefully there won't be any confusion. So just to paraphrase what I said, just this one time on Friday, 4 p.m., ran through 111, if you missed any homework assignments, any quiz, or if you're not happy with your grades, you have this chance to have a makeup for those. But this is like this one time. After this, if you miss a quiz, I assume you didn't want that grade. Okay? So now, I'm going to talk about intermolecular forces. We mentioned this briefly in 2 sessions ago. And can anyone tell me what was the name of intermolecular forces? We studied 3 different types. Does anyone remember? Hydrogen bonding, yes. Dipole, yes. Van der Waals. What was the other name of van der Waals? London dispersion, right? So I was just like thinking about how I can teach this concept the best. So I was just like, I was like talking about like dipole, and I was like, does the students know what is dipole? What is a dipole? Can anyone tell me? And I have like the answer on the board too, so you're welcome to look at it if you want to. But can anyone tell me what does dipole means, just as a word, even out of like chemistry? I guess inside chemistry context. But what is dipole? When I say dipole interactions, what do I mean by dipole?
2 poles or 2 charges.
Exactly, 2 poles or like 2 charges, right? So and I have like these listed here too, and I use my red pen. So pole, first of all, it has like several different meanings, and I had to go down like, when I had like in Merriam-Webster dictionary, one of the meanings is like 2 terminals of an electric cell, like battery, generator, or motor, or one of 2 or more regions in a magnetized body at which the magnetic flux density is concentrated. So I'm not going to ask you exactly these definitions, but I just want you to know when we say dipole, it means that we have like positive and negative charge, and di here means like twice, twofold, double, right? And if you remember di, we say like dimethyl, 2 methyls, right? Anyway, So when we say dipole, it means that we have like a positive charge and negative charge. And can anyone tell me what was a polar covalent bond? We talk about covalent bonds, like polar and non-polar. Can anyone remember what was polar? Exactly. Unequal share of electrons, or what did you say?
I just said unequal sharing.
Okay, what did you say?
Unequal sharings of electrons.
Okay, I thought you said two different things, but it was like the same thing. Uneven share of electrons, or like, we have like positive charge on one side, negative charge. So if we have like elements that they have like different electronegativity, they attract, one of the elements attracts the electrons more. So it becomes like slightly positive, slightly negative, right? The one that is more electronegative. So, as we said, polar covalent bonds is covalent bond in which the electron pair is not shared equally between the two electrons, or between the two atoms, sorry. So, and as you can see, when we say polar, it has the word pole in it. It's kind of like good to, kind of think about these things, and then we don't confuse them if we know where they came from linguistically. Does that make sense? Any questions? As I said, sometimes I forget to ask any questions, but if you have any questions, just raise your hands. So don't worry. Okay, and here again, because this table is really important, I included that again. We have like electronegativity of some common elements. Remember, fluorine has like the most electronegativity, and also oxygen and nitrogen. You see that these are like darker blue, I guess. And can anyone remember what type of bonds fluorine, oxygen, nitrogen of one atom can form with hydrogens of other atom? Hydrogen bonding, right? So these elements are really electronegative, remember. And can anyone tell me, I guess, is the following statement true or false? Carbon and hydrogen have like really similar electronegativity. True, remember? So don't be confused by the numbers. Numbers are slightly different, but still we consider them to be really equal, or like fairly close, or like equal. Okay, and you see that like metals, especially like lithium, sodium, potassium, beryllium, magnesium, calcium, these are like not that much electronegative, and we use another word for them. Can you remember when electronegativity decreases, what increases? Electropositivity, right? Okay, so now here, this is like, what color I choose? Okay, here is carbon, right? Here is oxygen. You see the electronegativity is like much different, 3.4 and 2.5. So this bond itself would be polar. And remember, the other one was H2O. So here we have hydrogen 2.2 and oxygen 3.4. Again, that would be a polar bond, right? Because elements have like different electronegativities. The first slide. So these, three. Usually we have like between fluorine, oxygen, and we're going to come back to the attendance slide. That we know this, we want to talk about dipole moment. So we talked about dipole, and it was kind of straightforward. We have like positive and negative charges, and that happens because we have uneven sharing of electrons, or like electrons are not shared equally between the atoms. So I have like some videos here from like Khan Academy website, and I really encourage you to watch them, because it explains really short videos, and this website is kind of like valuable in all other courses too. So if you didn't know something, this is kind of like good resource to refer to. And also I included a link for more information if you want to look at them. And here, well, that I have basically what I got from those resources that I told you. I realized that it's probably better to have like more information about like dipole moments, and so on and so forth. So we said that dipoles have like positive and negative charge, and they happen because the elements have like different electronegativity, right? So dipole moments occur when we have like separation of charge. And there are two different factors that affects dipole moment. So one of them is differences in electronegativity, what we just said, right? So for instance, if you have like hydrogen, right, and fluorine, so they have like different electronegativity, electrons are not shared equally between them, and we'll be having like separation of charge, so we'll be having like dipole. They form a dipole, and we have like a dipole moment between them. And also, the larger the difference in electronegativity, the larger the dipole moment. And it kind of makes sense, right? Because if one element like fluorine has a really large electronegativity, it attracts electrons more. But if you have like carbon that is much less electronegative compared to fluorine, it doesn't attract electrons as much as fluorine. Does that make sense? The other thing that is important is the distance between the charge separation. So that is also a factor when we're considering dipole moment. And also, I wrote this equation here again because it helps you understand that we have two things that are important when we're talking about dipole moment. One of them is like separation of charge. The other one is like the distance between the charge separation. So the dipole moment is a measure of the polarity of the molecule. And you see that, for instance, if we have like, I guess this table, we said if we want to have like a polar molecule, or if we have like, you know, when we consider dipole moment, which is a measure of polarity of the molecule, we have two factors. One of them is the charge, difference in electronegativity. The other is the distance. And does anyone know what is a vector? So in general, vectors, you know, kind of like, so this goes out of the scope of our course, but in general, vectors have like magnitude and also direction. So this is like a vector. It has a direction and it has like magnitude. I can tell you that the number here is like 2 meter or like centimeter, depending on what unit I'm working on. And I can say the degree here is like 45 degree. Okay? So here, this RI here is a vector that has like magnitude and also directions. The distance between the charge separation charges, the distance between the charge separation. So that is also a contributing factor. Just remember this equation here, that it was like charge and also distance between the distance of charge. I have like some structures, okay. So we have like CO2 and also water, H2O, as some examples. So if you just look at each individual bond, here we have like a double bond, right? Or like 2 double bonds. Here we have like a single bond. And if you just consider carbon and oxygen, is this bond by itself polar or non-polar? It's polar, right? Because carbon and oxygen have like different electronegativities, right? And if you go back here, so all the individual bonds are polar, but this compound here, carbon dioxide, CO2, is not polar, and H2O is polar. Can anyone tell me why we have like electronegative bonds, or like we have like polar bonds in both, but one of them is polar, H2O, the other is non-polar? Why is that?
Because it's linear, the geometry.
Yes, it's because of geometry, but what about the geometry that makes it? So although it's linear, why? double bond? Not necessarily. We can have like molecules with double bonds. Anyone? So remember, okay, so here we have like this R that I just mentioned. One of them is like, I just call it positive A, as like a just, you know, that it has a magnitude and is positive to the east or like to the right. And here it's like minus A. So it's the same amount of this A, the number, but it's to the opposite direction. So when we add these two vectors together, the result would be 0. Does that make sense? And again, I don't expect you to know things about the vectors in general, but I expect you to know that, you know, when we have this structure, they are like, you know, they cancel each other out because of the geometry of CO2, which is linear, that your friend mentioned. But this is kind of like the reason why CO2 is nonpolar. Does that make sense? Any questions? But that is not the case for, like, you see, and we have like these arrows towards the most electronegative elements. So now remember when we wanted to write like polar covalent bonds, one way was like to have an arrow, and the arrow itself would be towards the more electronegative atom, right? But if I do the same for H2O, right, these two vectors, they won't cancel each other. So that's why H2O is polar. But if the geometry was somehow that, again, those vectors were, you know, the same magnitude but opposite direction, it would be again nonpolar. Does that make sense? Kind of what I'm saying? Any questions? Separate, like kind of. Okay, so now here are some examples of nonpolar molecules with polar bonds. So these geometries, if you just remember these types of geometries, right? Kind of like, you know, CO2 is the linear, and then we have like this trigonal, square, and I don't ask you to know the names, you know, kind of like just help you to distinguish like non-polar molecules. But most of the molecules that you're going to encounter, I'll talk about them and I tell you. So for instance, in the quiz or like your homework, I'm going to ask about CO2 and H2O. So things that I talk about in the class. So you don't have to worry that much about molecules that you never saw. Does that make sense? Okay. So everyone's good with dipole moment? Is it like clear? So can anyone tell me what are the factors that contribute to dipole moment? Yes?
Differences in electronegativity.
Uh-huh.
And distance.
And distance. So how the distance between those, you know, we have, you know, kind of like this geometry can be CH4. And C and H, I told you that they have similar electronegativity. So CH4 and polar or non-polar molecules, right? And again, you know, these. Okay. So now those things being said, again, you know, I have like a video that I encourage you to watch. And here is kind of summary of what we talked about. So when we talk about like London dispersion, we can also call them instantaneous or temporary dipole. And in this video that I listed here, the person that is talking about like instantaneous dipole or London dispersion, he, you know, draws like the elements and then their electron distribution. And basically what he does is that, for instance, if you have just like one hydrogen atom, right? So you have like your nucleus and then you have like this electron density around hydrogen. So do you remember that based on like the different theories of an atom that we mentioned, what was the most established model that can describe the motion of electrons around the nucleus? Can anyone remember? We studied or you studied, in your elementary chemistry that there are different models, right? But what is it actually? How electrons are around nucleus? What is the most established model or theory? So Bohr was, really good established model, but it had some flaws. Do you remember what was it? We had quantum mechanical model, right? And then we talked about orbitals. Do you remember what was orbital?
Probability map.
Yes, probability map. What did you say?
I was going to say the shell that the electrons kind of stick to.
So the shell was the Bohr model. But the quantum mechanical model was saying that if I have a hydrogen atom and I have the nucleus, I cannot tell exactly, hydrogen has one proton and one electron, right? So I cannot tell exactly where that electron is. So we cannot exactly say it's here or here or here, and kind of to demonstrate it here for people that are watching at home. If I have a nucleus of hydrogen, I cannot say if the electron is here or here or here or here, right? And then we were saying that we have s orbital because it can be anywhere around not anywhere, but it would be around the atom, around the nucleus, and we cannot exactly tell where it is. So in general, if we have this nucleus here, this electron can be here or can be here or can be here, and at some points, at some instances or temporarily, this part of the atom might have that electron, and it would be slightly negative. So the other side, because it doesn't have that electron, would be slightly positive. It doesn't have, I guess here we have this electron, here we don't have it. Or for chlorine, for instance, another example that it has more valence electrons, 7, I can demonstrate that better. So at some point, this chlorine atom can have a slightly negative charge because there are more distribution of electrons on the left side, and it would be the other side slightly positive. Does that make sense what I just said? Right? So now if I have two chlorine atoms next to each other, at some point because now here I have a slightly positive charge, here, that positive and negative attract each other, right? So now, since this side of chlorine, this chlorine atom is slightly positive, it induces negative charge in the neighboring atom. So now it attracts more electrons here, so here becomes slightly negative. So as a result, this part becomes slightly positive. So we call these induced dipole, or we call them instantaneous dipole, or temporary. And there are different categories of molecules and atoms that can have London dispersion. And in general, so let me first say this. So they are often found in halogens F2I2. So basically, most of the time, if you have elements that they're the same and they're non-polar, you have London dispersion. So one category can be halogens, F2I2. Noble gases also can have dipole, right? Because again, for any element that you write by itself, it can have it has electrons distributed around them, and instantly at some moment might some part of the element has more electrons, so it would be a slightly negative, slightly positive. So they can have, again, noble gases also dipole, induced dipole, or the London dispersion. And also non-polar molecules, like such as carbon dioxide. Hopefully you can see the carbon dioxide. I mean, as I said, anything that I write, I post on Canvas, and also I include the slides without me writing on them, so you can read them. And I include these ones too, just you have them. And also methane. And methane is like CH4. And again, because of the geometry that methane has that we listed previously, also non-polar. And London dispersion forces are part of van der Waals forces or weak intermolecular attractions. So now I ask you a question. So I told you that, H2O molecules, they are like polar, right? So do you think that still H2O molecules, between them, they can have London dispersion? How many think they can? How many think they can't? So you see, this phenomenon that we talked about here, like instantaneous positive or negative charge, technically it can be for all the elements, right? So even if you have like hydrogen of one, hydrogen in water and then oxygen from the other water molecule, technically they can still have London dispersion. But since hydrogen bonds and also like dipole-dipole interactions are like much more pronounced, we kind of can just like ignore London dispersion. So if we want to quantify and write these forces between them, probably London, and then we have like, your book listed the exact order of these numbers. And as I told you, anything that I don't know off the top of my head, I don't expect you to know. But I expect you to know that London dispersion is like much smaller than hydrogen bonding, and hydrogen bonding, has like the most pronounced intermolecular forces. So if you have like three terms, like London dispersion, dipole-dipole, and like hydrogen bonding, this London dispersion term would be really, really small. So you can just like, don't write it. But technically they have that as well. Does that make sense? But for instance, F2, like fluorine molecules, they won't be having dipole-dipole or hydrogen bonding between them. They have only London dispersion or van der Waals interactions. Any questions so far? Is this clear, the lecture? Good. And so now we want to talk about dipole-dipole. And as you see, I'm just advertising for Khan Academy website. So I think it's really useful. So I encourage you to watch the video to even like better understand what I'm talking about. So now we want to talk about dipole-dipole forces. So we talked about instantaneous dipole-dipole, right? Or like induced dipole. For like dipole-dipole, those forces are between molecules with permanent dipoles, like basically polar molecules. And I told you, for instance, CO2 is not a polar molecule, remember? Or like methane is not a polar molecule. But if you have a polar molecule, the interaction between them would be dipole-dipole. Okay? For molecules of similar size and mass, the strength of these forces increase with increasing polarity. So if you have like, molecules that are like similar in size and mass, you can just compare the strength of, their polar bonds and like their polarity in general and compare them. And as we just talked about, polar molecules can also induce dipoles in non-polar molecules, resulting in dipole-induced dipole forces. So I guess we didn't talk about this specifically. So if we have like, for instance, fluorine, right? Or like, let me see. If we have, for instance, what is we have already here? So for instance, HCl, right, is like if you have like HCl and HCl, the interaction between them would be like dipole-dipole, right? Or like water, and we talk about water that they also have like hydrogen bonding, but again, the interaction between water and water would be like dipole-dipole. But if we have like, a dipole or like a polar molecule, and then we have like a non-polar molecule like CO2 or like CH4 or like N2. So these are like non-polar molecules. This is like polar. Again, because this molecule is polar, it can also, induce charge or kind of like causes charge separation in non-polar molecules with the same electron distribution that we just talked about, because one part of this molecule, like oxygens, are like have like partial negative charge. So if we have them in contact with like, for instance, N2, let me have like H2O. So this is like a slightly negative, this is like partial positive, right? So if we have it, next to nitrogen molecule, so now this nitrogen, because here we have like a slightly negative or like partial negative, here this nitrogen would be slightly positive because like opposite charges attract each other, right? So now because this is like, negative, the other atom would be slightly, so because this is positive, this would be slightly negative. So what I'm saying is that if we have like a polar molecule and non-polar molecule, the intermolecular force between them would be dipole, induced dipole. So when we say induced dipole, it means that permanently they don't have dipole-dipole interactions between them, but temporarily, because they're next to a polar molecule, they can have like temporary charge. Does that make sense? Good. Molecules. Okay, so here again is like your book demonstration, and as I mentioned at the first slide, anything that I talk about and include is from your textbook, whether I use like the slides that the publisher gave me, and most of the time I just like write things from your book on these slides, and the times that I'm not using those, I just cite the website so you can refer to them. So anything that doesn't have citation is from your book. So this is kind of like a good demonstration of dipole-dipole. You have like partial positive, partial negative, and then when you want to write, these partial charges next to each other, remember they should attract each other. You shouldn't have like negative here, because negative and negative, they repulse each other. Does that make sense? So this is how molecules come next to each other for like dipole-dipole. And these are like some examples for like, CH3Cl and, CH3Cn. So these are like examples of dipole-dipole interactions. And remember, these interactions are intermolecular. They are like between two molecules. Okay, we're talking about like, if we have like a water molecule and another water molecule, interactions, between molecules, so intermolecular interactions. So if you want to depict these forces or interactions, you have like one molecule, another molecule, and then you have like this, dotted line between them to show the interaction. Any questions so far? Good. Have our forces. Okay, hydrogen bonding. Again, like before, I have like a video here for you. And in general, hydrogen bonding is a type of dipole-dipole interaction. So if I give you a question in your quiz or your exam, I make sure that I term the word so it won't be confusing. So I don't say, what interaction or intermolecular forces exist between HF and NH3 molecules, and I give you like dipole-dipole and hydrogen bonding, and I meant hydrogen bonding because basically hydrogen bonding is type of dipole-dipole. Does that make sense? So remember that hydrogen bonding is a special type of dipole-dipole that occurs between the lone pair of highly electronegative atom, and lone pair, remember, is like non-bonding electron pair. So lone pair of the highly electronegative atom, and usually they are like fluorine, oxygen, nitrogen. Remember that electronegativity table that I showed you in the hydrogen atom in NH, OH, FH, right? So first of all, it's hydrogen bonding, so we should have hydrogen, okay? And we should have one of the elements of fluorine, oxygen, nitrogen. Does that make sense? So the interaction between like, HF and H2O, these can form hydrogen bonds between them, or like just water and water, or like NH3 HF, or like NH3 water. Any combination can be, hydrogen bond. But remember, the hydrogen should also be in NH, OH, FH bonds. So hydrogen bonding cannot be between like, fluorine and, hydrogen in HCl, for instance. So it would be like kind of like these combinations most of the time. And these are like some examples of hydrogen bonding: water, ammonia, and HF. Any questions? Okay. We can do this. And here again is the definition that your book presented, and we're not talking over, don't talk about like the orbital interactions and like the electron density, but you know the definitions. That hydrogen bonding is a complex interaction that includes dipole as well as orbital interactions, and we talked about this a little, right? We have like the lone pair electrons from like electronegative atoms, so this is what it means, and the transfer of electron density between molecules. So basically interactions between hydrogen when in high HF or like HN or like HF, and lone pair electrons of like fluorine, nitrogen, or like oxygen. Okay? And remember, these specific hydrogen bonding that we're talking about is intermolecular. So it would be between like this hydrogen here and this fluorine. Okay? Between the molecules. And here is like the range that is like between 5 to 25 kilojoule per mole. As I said, I don't ask you the number, but I ask you what is the strongest intermolecular force. And then I say hydrogen bond, London dispersion, van der Waals, dipole, which one? Hydrogen bonding is like the strongest, okay? Structure. And again, here you have like a nice picture depicting like this type of interactions that we, went through them in the class like 2 sessions ago. Okay. And here is kind of like the summary of what we talked about before and now. And remember that, so many physical properties of molecules are dependent to their intermolecular forces. And for instance, boiling point depends on intermolecular forces. And if we just talk, if I tell you how do you relate boiling point with intermolecular forces, does anyone have any ideas how to relate them? Or how to interpret if I tell you I have like, two different, compounds, or like, how can we relate intermolecular forces to boiling point? Yes?
The higher the intermolecular force, probably the higher the boiling point will be.
Exactly.
Yeah.
So, because when we want to boil something, we should break the intermolecular forces, right? So if atoms, or like molecules rather, or atoms of different molecules, you know, they have like strong intermolecular forces. We cannot break them. When we want to boil something, we want to break the bonds, right? So if they don't have, you know, a high intermolecular forces, or like they are like loosely attached to each other, just with the little heat that they give to that substance or like the compound, the intermolecular forces breaks, right? But if they are like attached to each other, you know, with really strongly, I should give so much heat in order to separate them. Does that make sense? And also solubility. Basically, the ability to dissolve in a solvent depends on intermolecular forces. And we talk about this in more detail in the next few slides. But it also depends on intermolecular forces. So why do you think, for instance, if I have oil and water, do they mix with each other? Why do you think is that? What's that? Density, yes, but in the context of what we're talking about. Yeah? So even if I have like a droplet of water, oil in water, or if I have like, you know, a full cup of oil, does it matter? Would one of them dissolve but the other one doesn't? So in general, you know, mass can affect, you know, but again, it doesn't change the fact that oil doesn't dissolve in water, right? But if I have like want to dissolve sugar in water, for instance, if I have like 1 teaspoon, or I have like, I don't know, a bag, so it differs, you know, at some point it would be like saturated and I cannot add more sugar. But in general, the reason that oil doesn't dissolve in water is that they have like different intermolecular forces. You know, water is polar, oil, we talked about hydrocarbons, they have like, you know, hydrogen and carbon, they are non-polar. So because they have different types of intermolecular forces, they won't dissolve in each other. And also the strength of the interaction between molecules is dependent on the overall shape, you know, of the molecule. So basically, these charge separations and these, you know, as we said, if you have like different structures, is dependent on the interaction, is dependent on the structure of the molecules, and intermolecular forces are also related to each other that we're going to talk about in the next slides. And here again, the summary that we have like different types of intermolecular forces: hydrogen bonding, dipole, and van der Waals and London. They are like the same terminology. Okay, now that we are like a couple of minutes early, let's just start the attendance so we don't have to rush at the end of the class.
When you pass me
You were coming back from whatever, like right by the lift.
Yeah.
So it's not due to March. So we can have insane.
We have almost 2/3 of the class present now. I don't know what that means.
Means it's Monday.
Yeah.
I have 2 different boards happening. That's Tuesday. That isn't.
But I can say
No, that you. Oh, okay. I know I talked about it with you.
Okay, so I'm going to post everything on Canvas. So if anyone didn't do the attendance, just I ask you to do it now, or if you cannot do it, just if it doesn't work, just come talk to me so I have your name so I can have your attendance checked. So here is one thing that we wanted to talk about, the structural effects on intermolecular forces that I just mentioned. So remember, if we have one thing that is really important when we want to compare different molecules is their surface area. If we have more surface area, like here in this molecule, which is like pentane, we will be having higher boiling point. But when molecules, they have more branches, they become more round in a sense. Here you see that this molecule, especially if you have the, you compare the structures here, you see that this molecule is more round compared to the other. And this is kind of one way to say that this molecule has less surface area. And when we have larger surface area like pentane compared to 2,2-dimethyl propane, we will be having lower boiling point. And the strength of the intermolecular forces depend on the amount of contact between the molecules, especially for dispersion forces. And I'm going to continue with this slide next session. And as I said,